Today in the workshop we'll be experimenting with Peltier cooling devices. I'll explain the Peltier effect and how these devices can provide cooling with no moving parts. We'll even make ice on the workbench. It's a really cool episode today, so welcome to the workshop. Hello and welcome to the workshop, and today I've got a bit of a different style of episode for you. Different in the sense that we aren't going to be using an Arduino or a Raspberry Pi. There is no code that we're going to be looking at. Instead, we're going to be looking at a relatively unique component, something called a Peltier cooler. Now, a Peltier cooler is a semiconductor device, and it works under the principle of the Peltier effect, which I will be explaining to you in a few moments. Now, as a cooler, this is really a heat transfer unit. It is capable of moving heat from one side of the device to the other, and as a result, one side of the device will get very, very cold, and the other side will get very, very hot. Now, Peltier coolers are far from just a scientific curiosity. They do have a number of practical applications. If you have a water cooler, either at your home or in your office, one of those ones that you put a big jug of water on top of, and cold water comes out the bottom, it is a Peltier device that is likely cooling the water for you. They're also used in portable air conditioner and dehumidifier units, although you wouldn't want to build a big air conditioner out of a Peltier device because it is not particularly efficient. The traditional type of cooler with coolant and all is much more efficient for cooling large areas. But for small personal coolers and for little fridges and freezers, the ones that you might take camping with you that run off of 12 volts, Peltier devices are often used for those. And they have a big application for semiconductor cooling. GPUs and CPUs on high-end computers often use Peltier devices to bring their temperature down. They're even used in spacecraft for that same purpose, because in a low-gravity or no-gravity environment, traditional cooling with pipes and all simply will not work. So they have practical applications as well. Today what we're going to do is literally a series of science experiments with a very popular Peltier device. And as you can see, I've got a lot of stuff over here on this workbench that we're going to be working with. So we're going to start off by learning about the Peltier effect and Peltier devices, and then we're going to take a look at a very common and inexpensive Peltier device. Let's take a closer look at the Peltier effect. The effect was discovered by Jean Charles Peltier in 1834. Peltier observed that current flowing between two junctions causes heating or cooling. The junctions were made with two different conductive materials. The original materials used by Peltier were copper and bismuth. Peltier noted that the temperature rises when the current passes from copper to bismuth. He also noted that the temperature falls when passing from bismuth to copper. This change in temperature at the junction is called the Peltier effect. A similar effect to the Peltier effect is the Seebeck effect. This was discovered by Thomas Johann Seebeck in 1821. Seebeck based his work on original research done by Alessandro Volta in 1794. And yes, Mr. Volta is indeed the person that the volt was named after. The Seebeck effect uses dissimilar conductors like the Peltier effect. The Seebeck effect produces voltage when exposed to heat. Both the Peltier and Seebeck effects are classified as thermoelectric effects. Modern Peltier devices are built using semiconductors. Alternate legs of P and N type semiconductors are arranged in a matrix. Conductive sheets are placed on the top and bottom of the matrix, and these provide electrical connections. The entire assembly is sandwiched between thermally conductive plates, which are usually ceramic. Passing current through the semiconductors causes the Peltier effect. The Peltier device that we will be working with is the TEC1-12706 and its part designation can be broken down as follows. TE is an abbreviation for thermoelectric. C indicates the size. A C is a standard size Peltier device, while an S is a small Peltier device. The 1 designates the number of stages in the device, or the number of layers. Most Peltier devices only have 1 stage. The 127 are the number of couples inside the device. These are the number of PN semiconductor junctions. And finally, the 06 indicates the maximum current rating of the device in amperes. Let's take a closer look at our Peltier cooling device. So here's my Peltier device, the TEC1-12706, and as you can see, there's not really very much to look at. It's basically a square block. This measures 40 millimeters on each side. It's got a red and a black lead on it for power, and not much else to see over here. Now on my module, when it's hooked up with the red and black, with red going to positive and black to negative, the side with the writing is the side that's going to get cold, and the other side is the side that's going to heat up. Incidentally, if you reverse the polarity on the Peltier device, it'll be the opposite. This will end up being the hot side, and that'll end up being the cold side. Now, as for which is hot and cold when the polarity is correctly hooked up, again, mine has the side with the writing being the cold side, but I don't think that's universally true, so you should probably test out your own Peltier device before you mount it into your assembly. But if you get it wrong, the worst thing you'll have to do is just reverse the polarity on the leads. So now let's go and start our experiments. Alright, now we know a little bit more about how Peltier modules work. Let's start using one. Now we're going to use the little module I just showed you to do 3 different experiments. The first experiment is simply one of powering up the module, which is quite easy. You'll notice it had 2 leads on it, and we're just going to apply 12 volts on it. It needs a fair amount of current, so we're going to be using my bench power supply for that. Now, we're going to apply power just briefly to the module, because what I want to show you in the first experiment is just how hot this module will get and how imperative it is to use heat sinking. In the second experiment, I'm going to add some heat sinking, and we're going to do the opposite. We're going to see just how cold this module can get once you've added a heat sink to bleed away the heat that's extracted. And for the third experiment, we're going to do something that's really more of just a scientific curiosity. A Peltier module can also produce electricity from heat, and so we're going to give it a test, hold a heat gun to it, and see if we can get some electricity out of our module. So let's begin with our first experiment. So here's my Peltier module. I've got it sitting over here right now. The side with the writing on this module is the one that's going to get cool, and the one that doesn't have any writing is the one that's going to get hot. Not all of them are like that though, so you might want to check your own individual module to make certain. Now, what I'm going to do is I've got my bench power supply over here, which you can sort of kind of see off the side over here. And I'm going to apply some current to it, but not for a very long time, because without any heat sinking, this hot side is actually going to get pretty hot. Now, I'm going to attempt to take a temperature measurement before I do that. And so I don't know if you can see that. It's about 20 degrees, 20.8 degrees Celsius. That's kind of around the ambient temperature of the workshop right now. And I'm going to turn this on just for a few seconds. And I can already feel it getting very warm. I'm going to turn it off right now because I don't want to destroy the module. And I'm going to try to take another reading, and over here is 63.7 Celsius, and it went up there just in a few seconds. And so that will give you an idea of just how warm the other side of the Peltier module is going to get. Now in this case, the cool side of the module is still a bit warm, and there's 2 reasons for that. First of all, of course, my arrangement here is conducting heat from one side to the other, but also without any heat sinking over here, the cool side is really not effective. It gets hot very quickly simply because of the heat on this side. And so next what we're going to do is attach a heat sink to this and see what the difference is. Now in this experiment I'm going to show you what the effects of applying heat sinking to the Peltier device is. Now I've got my Peltier device mounted onto a heat sink, and I've used some of this thermal compound between the device and the heat sink to make the heat transfer even better. I've also tie wrapped it to the heat sink so that everything is pressed down firmly, and the tie wrap shouldn't be conducting much heat from the sink up to here. So this is the cool side of my device here, and the warm side of course on the heat sink. Now I've got this whole assembly sitting inside some water. I've got a pan with some water inside it. So I'm going to turn on my power supply, and right now I can already feel this is getting quite cool. I'm going to take a little bit of this water, not too much, that should be enough there, and just drop it onto the top of my Peltier device. That should be fine. I'm going to start a timer over here, and I'm going to speed the video up a bit so that we don't actually have to sit here for the entire thing, and we'll watch what happens. Alright, 3 minutes have gone by right now, and let's take a look at the water that I dropped on top of my Peltier device. And oops, there's a piece of it went there. This isn't water anymore, guys. This, here we go, is a piece of ice. Now, in order to make ice, that had to be down at least at 0 degrees Celsius or colder, and it made the ice, it actually started forming, I noticed, at about the 1.5 minute mark. So there you see the effect of heat sinking. The Peltier device is actually dropped below the 0 mark and is capable of making ice. Now for this experiment we're going to do something a bit different with the Peltier device. We're going to use it to create electricity. It's capable of doing that, although it doesn't create a great deal of electricity, so it doesn't have a lot of practical applications. If you were to hook a number of these up in series and parallel, you could probably get enough electricity to drive a small device, and it might be useful in some high heat environment where you're trying to recapture the heat energy and turn it into electricity, although there are better ways of doing that. But nonetheless, it is an interesting, if not amusing, experiment. Now, it's a very simple hookup. I've got the same Peltier device we've used before. Right now I've got the side facing toward me that normally produces the heat, although you can apply heat to either side, and the effect will be, if you apply it to the other side, the electricity will be in the opposite polarity. Now I'm using my analog multimeter instead of one of my digital multimeters for this, and I just did that because I think visually it is a more appealing type of effect. I'm going to set this right now to the 1 volt full scale. So again, we're not getting a lot of electricity out of this, so when this meter is pinned over here, we've got a full volt of electricity. And I've got my heat gun, and I'm going to heat up my Peltier device. And as you can see, we're getting some voltage over here. In fact, we're about to pin it on the 1 volt scale. Let's just move that up to the 3 volt mark. So now 3 volt full scale. I'm heating it, and it's going up. It's almost at 1.5 volts. There, it's at 1.5 volts right now. So I've got barely enough electricity to even light an LED up right now. But as you can see, not a great deal of electricity, but it does indeed produce electricity when it is heated. So this is yet another effect of the Peltier device. Now, to finish off our experiments with the Peltier module, I wanted to take a look at this gizmo, and I know it's a pretty weird looking gizmo. It looks kind of science fiction-y, like something out of the Back to the Future movie or something, but it's not a flux capacitor. What it is it's a Peltier module, just like the one we looked at, with a number of heat sinks and fans attached to it. And this assembly is very commonly available on eBay, which is where I got this one, and they're very, very inexpensive. In fact, I got this one along with a 12-volt 6-amp power supply, which I'm not going to use because I'm using my bench supply, but the cost of the whole thing wasn't much more than the cost of the power supply. So if nothing else, I've got some fans and heat sinks over here and a Peltier device at a real bargain. So I want to hook this gizmo up and we'll see if we can measure the cooling effect of it. So let's go put it on the workbench and do that right now. So here's a bit of a closer look at this unit. As you can see, it consists of a number of different devices. The Peltier device is actually back in here. I'm not certain if you can see it. It's kind of wafered in between these heat sinks. There's a heat sink on the cold side over here. This is the cold side of the Peltier Effect device. And it's got a fan on it, and this fan is blowing the air out. So the cold side is cooling down this heat sink and then blowing out the air. Now, they've got a heat sink mounted on the other side of it, right over here, and another big heat vent over here, and that is attached with a series of heat pipes, and the heat pipes are also on this side of it as well. And there are two fans over here, and the direction of airflow is this way. So this one is taking in the ambient air, and this is expelling the hotter air. So we should get cool air coming out over here and warm air coming out over there. So let's turn this beast on. It's being powered up with 12 volts. Everything here runs on 12 volts, the Peltier device and all of its fans. And I can feel some nice cool air coming out over here. Now it's a little difficult to get a good temperature reading. I have to kind of hit it from the bottom, I think, to try that. Let's see if I can get one. It's getting cooler. I've got a reading now of 17.4, which is lower than my ambient. Let's see. Now I'm still getting readings of about 17. I actually have, on some of my experiments, had it down as low as 15. It's a little hard to hit the right part of it. Another thing that you probably can't see too well in the video, but I'm getting some condensation over here on the top of this, and that's actually condensation from the moisture that's in the air right now that's coming off. So this is also doing a bit of a job of dehumidifying the air as well as cooling it. So this device could be used in a project if you were able to isolate this section from this section, because I do have some warmer air coming out over here, and so you'd need to have an intake and an exhaust over here, and then your nice cool air coming out on this side. So a interesting use of the Peltier device. And so this brings us to the conclusion of our DroneBot Workshop science experiments with the Peltier Effect. And I do hope that you enjoyed the video and that perhaps you've learned something about the Peltier Effect and have some ideas for applying a Peltier Effect device in your own projects. These devices are very inexpensive, although again they're not that efficient, but they can be used for cooling down things. So maybe your Raspberry Pi 4 is getting a bit hot. You could try using a Peltier device on that to supercool it. Maybe your own high-end computer needs some cooling down, or you might want to pick up that same gizmo that I picked up on eBay and build a personal cooler out of it. As long as you can find a place to vent that heat, it should work relatively well. Now, if you'd like some more information about the Peltier Effect device that I used today, or about the Peltier Effect in general, just check out the article that accompanies this video on the dronebotworkshop.com website, and you'll find a link to that article right below the video. While you're on the website, website. If you haven't already, please subscribe to my newsletter. It's not a sales letter. I promise I won't try to sell you anything. I won't even try to sell you a Peltier Effect device. Instead, this is my way of keeping in touch with you and letting you know what's going on in the workshop. If you haven't subscribed to the YouTube channel, of course, well, what are you waiting for? Please do that. And finally, if you'd like to discuss this or anything about electronics or microcontrollers, the best place to do that is on the DroneBot Workshop forums, and you'll also find a link to the forum right below this video. So there's a lot of places you can go from here. So until the next time, please take care of yourself, please keep cool with your Peltier Effect device, and I hope to see you again very soon here in the workshop. Goodbye for now.